Hello, I'm Austin Zilke, and I'll be presenting about spinning rotor fluid flow and thrust produced. Vertical rotor aircraft are extremely prevalent and useful in society today. Examples include helicopters used for military, law enforcement, and medical purposes, or at a smaller scale, drones and multicopters used for aerial imaging, surveillance, recreation, or even as future flying taxis. It is crucial to understand how spinning rotors can produce enough thrust to allow the aircraft to hover. The aim of this project is to further understand the thrust forces behind spinning rotors by using StarCCM Plus to visualize the fluid flow around the spinning rotor, in addition to calculating thrust produced by the rotor in a steady-state simulation and comparing it to experimental wind tunnel values. By confirming these simulated values as accurate, the next step of this project is to utilize an implicit-unsteady simulation in StarCCM Plus to determine if the accuracy changes. I hypothesize that an implicit unsteady simulation will be more accurate in determining thrust produced by a spinning rotor at the cost of being more computationally expensive. The rotor model is perhaps the most important aspect of the simulation. In order to be able to properly validate simulated calculations with known values, wind tunnel data must be available for the rotor of interest. The selected rotor is a 5.5-inch diameter model, shown to the right. Both the IGS model and wind tunnel data were found in a thesis made available online about aerodynamic performance characterization of leading-edge protrusion on small propellers. The next step was to model the rest of the simulation for a steady-state StarCCM Plus analysis. A cylindrical fluid domain with a 0.5 meter radius around the rotor, extending 0.2 meters upstream of the rotor and 0.5 meters downstream of the rotor, was created. This cylindrical fluid domain was modeled using half-plane symmetry to make this simulation more computationally efficient. In addition, a domain was modeled to simulate fluid rotating directly due to the rotation of the rotor. It was modeled as a 0.15 meter radius cylinder, extending 0.1 meters upstream of the rotor and 0.2 meters downstream of the rotor. All three models were imported as parts with medium tessellation densities and subtracted to create a fluid domain minus rotation domain part and a rotation domain minus rotor part, shown to the right. The mesh was created using the finite volume method, with an automated mesh utilized. The mesh consisted of a surface remesher, polyhedral mesher, and a prism layer mesher. With a base size of 0.05 meters, 10 prism layers were chosen, with a prism layer stretching of 1.2 and prism layer total thickness of 0.015 meters. A couple surface controls were then added to increase the mesh accuracy. A section view of the produced mesh is shown to the left. A detail of the rotor mesh is shown above. The model was chosen next, based on the Navier-Stokes governing equations. These equations were to be solved by StarCCM Plus in a 3D space, as the models were three-dimensional. This simulation was to be solved as steady state, with ideal gas air making up the fluid domain. Compressibility of the fluid is present in the simulation, so coupled flow was chosen. For computational efficiency, the flow is assumed to be inviscid, with the model defined and the free stream velocity of the domain set as 10 meters per second. Then, boundary conditions and interfaces were applied. The inlet and free surfaces of the fluid domain had a 10 meters per second velocity inlet boundary condition. The outlet of the fluid domain had an atmospheric pressure outlet defined. The left and right side symmetry planes of the fluid domain and rotating domain had a periodic internal interface applied, and this kind of allowed for the rotation to be periodic and not just both ways. Where the inner surfaces met the outer surfaces between the fluid and rotating domain mixing plane interfaces were also applied. To introduce motion into the steady-state simulation, a rotating reference frame was created about the z-axis with a rotational speed of 8,000 RPMs to match available wind tunnel data. This rotating reference plane was applied to the rotating fluid domain. The second StarCCM Plus simulation utilized an implicit unsteady model to analyze thrust produced by the rotor over time to compare to both the steady state and experimental values. Following a guide by the BYU Flow Lab, a bullet-shaped fluid domain was created around the same rotor as the previous simulation. Below the rotor, a fully revolved cylinder with a radius of 10 times the rotor's diameter and extending 20 times the rotor's diameter was created. Above the rotor, a hemisphere with a radius of 10 times the rotor's diameter was also created. A rotating domain was additionally created around the rotor as a cylinder, with a diameter of 0.16 meters, extending 0.02 meters upstream and 0.01 meters downstream of the rotor. In addition, a mesh refinement domain was created additionally as a cylinder around the rotor, with a 0.2 meter radius and extending 0.025 meters upstream and 0.125 meters downstream of the rotor. The rotor was created as a part with tessellation density defined by the BYU Flow Lab guide, and both the fluid, rotating, and refinement domains were created with very fine tessellation densities. Like previously, part subtractions were used to create a fluid domain minus rotation domain part and a rotation domain minus rotor part, shown to the right. Two parallel meshes were created. The first mesh was created for the fluid domain minus rotation domain, using surface remesher and trim cell mesher. The second mesh was created for the rotating domain, using surface remesher, polyhedral mesher, and prism layer mesher. A section view of the executed meshes are shown to the right. A section detail of the rotor meshing is shown below. The model for the simulation was chosen similarly to the previous one, with the only key differences being an implicit unsteady solution over time and a turbulence model being chosen instead of inviscid. A k-omega turbulence model was chosen to best model flow in this simulation. A Mach number of 0.02888 was calculated given the free stream velocity of 10 meters per second through air at sea level. Boundary conditions and interfaces were then applied. The fluid domain free stream was given a free stream boundary condition. A velocity inlet boundary condition of 10 meters per second was applied to the fluid domain inlet. A pressure outlet was applied to the fluid domain outlet. An interface was applied to the fluid minus rotation and rotation minus rotor default domains. The rotational domain was given a rotational motion specification at a speed of 8,000 RPMs as previously used. A time step of 1.25 times 10 to the negative fourth seconds was chosen, with a max number of 180 steps, which gives the rotor 6 degrees of rotation per time step, which equates to 3 rotor revolutions per simulation. After letting the steady-state simulation run for 250 iterations, the residuals plot provided evidence that the values had approached convergence. In order to validate the simulated results for accuracy, the previously mentioned wind tunnel data required interpretation. For the rotor model used, an advanced ratio is calculated to be 0.53686 from the advanced ratio equation shown below. By looking up this advanced ratio in the wind tunnel data shown to the right, and looking at the value for 8,000 RPMs rotational speed of the rotor, a thrust coefficient of 0.035 was determined. Using the thrust equation shown below and the experimental thrust coefficient, an experimental thrust value was calculated to be 0.2903 newtons. Given these values, the steady-state simulation can be validated by looking at the thrust plot on the next slide. As the solution converged, a thrust of approximately 0.3 newtons was calculated. Here is the thrust plot. With the thrust calculation validated, flow velocity seen of the rotor is shown right here. You can kind of see high velocity right below the rotor and how the fluid velocity kind of goes down, and that is what leads to thrust. After letting the implicit unsteady simulation run for 180 steps, the resulting residuals plot showed that none of the Navier-Stokes equation solutions had diverged. This residual plot is shown to the right. The simplified thrust plot's line of best fit estimated an average thrust value of approximately 0.305 newtons, which is also validated by the wind tunnel data. And this resulting smoothed thrust plot from the rotor is shown right here. It was fit using a linear line of best fit, and it was smoothed by neglecting the first 20 time steps where there were higher residual fluctuations. The original thrust plot from StarCCM Plus is shown right here. The resulting flow velocity seen, calculated by the implicit unsteady simulation of the rotor, is shown right here. It's very similar to the other one. You have the high velocity of the fluid right below the rotor. You have a little bit of stagnation on top, and then you have fast velocities below it, which is what leads to the thrust. Looking at the above results, the percent error can be calculated from the percent error equation shown to the right. For the steady state simulation, the percent error was calculated as 3.34%. This error is impressive given the assumptions made for the simulation to reduce computing power needed. Surprisingly, the percent error for the implicit-unsteady simulation was calculated as 5.06%, which is a higher error than the steady-state simulation. This disproves the hypothesis. All in all, utilizing StarCCM Plus is an effective means for creating visuals to better understand how rotors generate thrust to produce lift, causing an aircraft to hover. Furthermore, it is an accurate method for calculating thrust produced by a rotor. With the validation of a proper model and effective meshing of said model, StarCCM Plus serves as a useful program for further development of untested rotors and their usefulness in the aerospace industry. With regards to the simulation results, one of the main sources of discrepancy between the experimental and theoretical results were the availability of computing power available. While the steady-state simulation was quite simplified to reduce computational resources necessary, the symmetric model and assumptions made still allowed for fairly accurate results to be computed in fewer iterations, about 250. Conversely, the implicit unsteady simulation was computationally more expensive as it modeled the full rotor and fluid domain, and iterated over multiple time steps. Due to my computational limitations, I was only able to simulate 3 revolutions of the rotor in a simulation that was run overnight. With further computational power, such as access to a supercomputer, a higher time step solution would be able to be computed, and error would be further resolved. Due to this aspect and my own computational limitations, I believe with an implicit unsteady simulation having a much higher amount of time steps, a more accurate thrust calculation would be computed. Furthermore, my hypothesis would likely be proven correctly. For further work, I would recommend carrying out the implicit unsteady simulation with more computing power to increase the accuracy of the thrust calculation. In addition, the use of overset meshes in StarCCM Plus could be utilized to test a different meshing method. In my research of different methods for simulating flow through a rotor, I was unable to find many resources available that describe best how to utilize overset meshing. Thank you.